Hello, my name is Moody, and I have been looking at the identification of lush from fluvial deposits at Flagstaff Rim, Wyoming by machine learning methods. So the deposition of the North American Lush Plateau that occurred during the Paleogene was initially believed to be very abrupt and caused by the climate change of the surrounding area. However, research has determined that it may have been more gradual and earlier than previously thought. This has been done by looking at grain size distributions of wind-transported loess and river-transported sediments, and they're very different from one another, to identify groupings within these distributions. And the aim of this study is to look at unsupervised machine learning algorithms to see if they're able to aid in the identification of the grouping of these patterns. So our study area of Flagstaff Rim, Wyoming, we can see our stratigraphic section here that is dominantly fluvial at the bottom with conglomerates and medium grain sandstones, and more aeolian at the top with finer grained material. For our machine learning methods, we use both dimension reduction methods and clustering analysis methods. In terms of dimension reduction, this is the process of taking high dimensional data and reducing the components so it can be more statistically analyzed and visualized, and we used principal component analysis and t-distributed stochastic neighbor embedding. For our clustering analysis for our actual grouping, we were able to use k-means clustering and spectral clustering. So if we take a look at our manual classification results, we can see that type A is our typical aeolian distribution. Type B is very similar to type A, but with a hump between 1 and 10 micrometers. Type C is our second aeolian variant with a hump between 100 and 1000 micrometers. And type D is our fluvial that has a lot of variance in grain size. When looking at our clustering groups with PCA dimension reduction, both k-means clustering and spectral clustering don't have very tightly bound groups. However, k-means clustering shows better defined boundaries than spectral clustering here. When looking at our t-SNE dimension reduction methods, our k-means clustering and our spectral clustering both had very tightly bound groups, but our boundaries for our groupings look a little bit better with our t-SNE dimension reduction and spectral clustering. When looking at our grain size distributions, our k-means clustering distributions look very similar to our manual classification results. Type A, type B here, type C, and type D with our fluvial. However, with our spectral clustering grain size distributions, cluster 1 and cluster 2 are both determined as type A distributions and are very similar to one another. The spectral clustering here didn't do as good of a job at picking out these grouping patterns, and cluster 3 and cluster 4 are the same. If we look at our stacked bars here, we can see that k-means clustering and spectral clustering are very similar to one another, but when compared to our manual determination methods, k-means clustering might have more similarities than spectral clustering here. Thank you for listening, and please let me know if you have any questions.